How many people are DBAs or data professionals, data engineers? Okay, that's the majority of the hands in the room so far. How experienced are you? Like, and let's not say it by years, right? Because there's doing the same thing 20 years in a row, and then there's continuing to learn and doing different things. So how many people feel like they're fairly new at what they're doing? Okay, that's fair. I'd say about 25%. How many people say they're, mid-level, moderate with what they're doing? Okay, good deal. And then how many people are my advanced users? Okay, do I have anybody writing the product? Because if you're writing the product, you are going to be bored. Yeah, of course. So this is a talk that I put together a long time ago. And one of the main reasons I put it together is I started off my life as a developer. I became an accidental DBA, and then I became a full-time DBA. And then I became a consultant, and then I went to work for Microsoft. One of the things that I found to fundamentally understand how to be able to get better performance out of indexes was largely how to be able to shape them correctly. Is there anybody in the room that would say, because a lot of people were data professionals, more developers? Okay, yeah, okay, so we've got about, I'd say 30% of the room. It's a safe space. When you always hear about, developers, DBAs, cats and dogs, and how they just, go at one another. It's in the US, that's kind of like the police and the fire department. Like they all show up and they all help if you're in trouble. My dad was a police officer. My grandpa and my uncles were firefighters. And so, they would always give each other heck. I mean, there were so many funny little things that I heard. I mean, not funny, haha, but like, if the firefighters really pissed off the cops, they'd boot their trucks while they were at the scene. So they couldn't move the trucks unless they called the cops again. And of course, the firefighters just loved to pull up to the donut shop and then block in all the cop cars so they couldn't pull out. They would just, little things like that. But the fact is, when it really hits the fan, it's a symbiotic relationship, right? That's a lot like what we're doing with DBAs and developers. It's a symbiotic relationship. The goal is to have an application that runs fast and to be able to have data that runs and retrieves it in a very fast format as well. And so those are key learnings, key understandings that we want to make sure that we understand. And it's really how we come together. If you sit down and you take the standpoint of no one was born knowing this. I remember being a developer and writing insanely bad SQL queries, passing them through an ASP Classic web interface and having a consultant walk by me and go, oh, that should really be a stored procedure. And I'm in my chair going, what in the heck is a stored procedure? So I may be up here talking to you about this now, but there's education, there's knowledge that we learn along the way. And the key thing is that we make sure that as we grow together, we share that knowledge. And remember, your journey at this point in time, for all my people who are advanced, for all my people who are mid-level, at one point in time was the new person in the room. So it's always good, whoever you're working with, be it a DBA or a developer, to put a little bit of grace in place as we're talking about some of these things and make sure people share the knowledge. All right, we're at 3:20. I'm going to start, and this is me. My name is Bradley Ball. It's good English, Irish name. I'm a mutt. I got a whole bunch of lineage in me. That's what we are in America. My last name is Ball. As a young man growing up, you may imagine, I got some nicknames. They were quite creative. And so when I joined the community, I just thought I would go with the name SQL Balls. And it would be very easy to remember. I've got a YouTube channel with a bunch of my friends, Tales from the Field. We do a lot of content. On Mondays, we do SQL-based content. On Tuesdays, we do an Azure Data Community Roundtable where we share the content in the community from the different creators in the community, blogs, videos, anything that people are producing. On Wednesday, I do this. I do a lot of Fabric content. I also occasionally do some of our SQL content as well. So I've got stickers up here. I know everybody comes to a conference and they want stickers. So I've got a ton of them. If you want some, please just feel free. I'm going to stick them right here. At the end of the session, you don't even need to talk to me. You can just grab one. But if you want one, I'll be around. All right. So what is our agenda? We're going to talk about classic structures, clustered indexes, heaps, non-clustered indexes, how to measure performance, making good changes, and avoiding mistakes. When we look at different index types, we have covering indexes, we have clustered indexes. This is what we're covering. Clustered indexes, heaps, non-clustered indexes. We're going to talk a little bit about filtering, covering, and unique, because situationally they will come up. I may not have a demo for everything, but we are going to discuss them. And then we're not covering column store indexes, in-memory OLTP indexes, full text indexes, XML, spatial, and we're mostly talking SMP, regular SQL Server. We're not talking MPP or Fabric or Synapse. There'll be a couple places where I have a little note where I go, this is going to be different over there. You would do this slightly different in these worlds versus what we would do in traditional SQL Server. One other thing, and this is very important. Don't feel like you have to wait till the end. This is your time. Your time is important and valuable. First off, thank you for coming in here and joining me. I'd like to get a picture of everyone, so if we could just, no. But I want to thank you for your time. So if you have a question, please raise your hand. I know we've got microphones around here somewhere. And feel free to say, Brad, Balls, Bradley, whatever you want to call me. Keep it within those three, though. I think we'll be pretty good. Not my middle name. Then I think I'm in trouble. But ask your question, because I want to make sure that we get to it. All right. So heaps versus tables. This used to be a bit of a holy war. And it was a holy war only because people were very much either Oracle DBAs, we were Oracle shops, or we were using SQL Server. I don't find that to be as much of the case as this used to be, but it did used to be the case. And so in Oracle, the default table type is a heap. In SQL Server, the default table type is clustered indexes. But there are good, valid reasons to use both of those. And even amongst any best practices you would ever hear, I will tell you this, the best practice is how you use something within your organization. If you are getting results and it works for you, that is a best practice. And nobody on a blog or nobody in a docs article gets to tell you to do something differently. And when I meet with customers and I work with them, that is exactly what I tell them. You know your data better than I know your data. If we sit down and talk for an hour or 5 days, it is nothing compared to the time you have put on the job spending with this data. You will always know your data better than me, and I must trust you when it comes to speaking about your data. So we want to make sure that we always follow the best practices of what we're doing with our data. So what is a heap? A heap is a base table. It's linked. We have an IAM page, an index allocation map, but there's no physical order to it. It's paper strewn about a desk. So that way we can just say, they're all there. They're definitely the papers. They're sitting on the desk. But if I want to find one, what have I got to do? I've got to look through every single sheet of paper. There's nothing to tell me, here's a shortcut method to be able to look at, to be able to find it. And so I've got to look through every single one of these things. Very important to keep in mind. Every operation on a heap is a scan. Now, we'll get to this. You could put a non-clustered index on a heap and you could get seek operations off of that. But if I am going against the physical base table itself, every single time I do anything, select star, where predicate value, doesn't matter. I am scanning that object. If it's a very small heap, no big deal. If it's a very large heap, could be a pretty big deal. Now, there are some valid reasons to be able to use these. We'll get those in a minute, but this is what the physical structure is going to look like. I have an index allocation map. Does everybody know what an index allocation map is? Raise your hand if you don't. Don't? There we go. Okay, so an index allocation map is a bitmap. We're going to talk about different bitmaps within SQL Server. Bitmaps are how we track things very, very efficiently, where we have 8 bits equals a byte, and we use them as ones or zeros to be able to flag if an indicator is the truth for something. We also use them to be able to chain things together. In an index allocation map, we basically have about 4 gigabytes that we get to track of individual 8K pages. And so if we do an operation on an index allocation map, and we have multiple index allocation maps to chain our tables together, especially because tables get larger than 4 gigabytes, this is how we find out this is the entire structure. When I say select star from, there's a metadata object that says, here's the name of the table they're using, here's the object ID associated with it, go get every IAM page with this object ID associated with it, and find this. Now, that's for a heap. Again, for indexes, we'll have statistics, we'll have some additional metadata that we'll look through, but that's for a heap. It's just this basic structure. So why would we use this? Loading of staging tables. It is an absolutely fantastic thing. I had a customer once, and they wanted to be able to load staging tables much faster. And the loading time of the staging table took 65 minutes. And I took a look at the staging table. It had a clustered index on it, and it had 3 non-clustered indexes on it. And I said, if we drop all of this and we put this as a heap, it's going to massively improve the performance of this. And he goes, well, but I referenced this object specifically after I load the data into it, and I need this index, and I need these non-clustered indexes. And I said, that's not what we want to do. I said, I get what you've got. Let's talk about what we want to do in the future. I said, I'm going to show you the performance, but what we really want to do is we want to load the data in a heap, then we want to do an incremental load of just that data you're loading into the table in the future. That's what we need to do to be able to get the best performant option that we possibly can. We took all the indexes off. We loaded it into a heap, and it took 34 seconds. And he went, wow, this is great. So what I'm going to do is I'm going to drop my indexes. I'm going to insert the data into a heap. I'm going to rebuild the indexes. And I said, well, in order for us to do that and know that's actually a viable option for you, what we're going to have to do is time the rebuilding of the indexes. And the rebuilding of the indexes took 67 minutes. So that wasn't a viable option for that table. So what did we do? We said, well, this is the table. This is the table you're using. Let's make a new process where we use a staging table. We load the data into that. We look at how we get an incremental load pattern going, and we incrementally load the data. That was, that worked out being a total of a 5-minute job that he had to process once a day. So that's how we saved that time. There's good, valid reasons to use heaps. Temp tables. Every temp table you create is a heap. You can put a clustered index on a temp table. I don't know if you know that, but most of the time you don't need to, because your temp table will not be large enough that you would need to have a clustered index on it or a where predicate value for that temp table. You may. I've had to do it before. There's some good valid reasons to be able to do it. But typically when we use a temp table is a heap. We create it, we get rid of it, we use it as an intermediary table, and we move on. Some issues: poor performance. If I have to scan something every single time, it's going to take a lot more IOPS. That's a longer query time. I had a gentleman I was working with in a retail store. We had to aggregate the results. We were loading flat files in from all these stores. This was literally just the tool that actually made that happen. We weren't actually inserting the data. But the history table, inserting the data into the history table took so long because of what they were doing, because they had to scan that to validate that the new data was there, and they were keeping a history of everything. Every time they loaded those tables, we put the right indexes in place for them to be able to use, and we dropped that operation from being a 65-minute thing, and they needed to get it done in 60 minutes, to sub-second. He was so excited. It's a grown man wearing cowboy boots, jumped up, clicked his heels. I'll never forget that sight. Walked away, pointed at my boss's cubicle, "This guy's great, keep him." I was like, okay, well, I'll use that in my review, right? But we got it down. As a matter of fact, the reason he was at my cube is when we first ran it, it was so fast, he ran up and he said, "You broke my process." I went, "What do you mean?" He goes, "You broke it. I clicked the button, it said done, it's broken." I went, "Well, hold on a second. Let's look in the table, see the history." No, we loaded everything from all 1,500 stores. That's why he was so happy. That's why he jumped up and clicked his heels, because using the right indexes makes things faster. Using a heap, scan operation every single time. So remedies: we changed something to a clustered index. That's not typically what I would like to see, but it is technically a remedy. If we have forwarding pointers, we can fix those by doing the update rebuild command. On older versions of SQL Server, prior to compression, so 2008 on up, when we introduced page and row compression, you could rebuild a heap. Before that, you could only add a clustered index, drop a clustered index to get rid of a forwarding pointer. Now, real quick, what's a forwarding pointer? A forwarding pointer is when, let's say I have a variable length field in a heap and I update that variable length field. The page is completely full. It's going to go, I don't have room here. So I'm going to hop over to a new page at the end of the allocation, but I'm going to leave a little post-it note: "I was here." That is a pointer to the page in the slot array where you can find me on the new page. A heap can actually have up to 2 forwarding pointers per record. So if I go and I update that record again, I now reallocate myself to the end again, leave another post-it note. I might have to do multiple hops. So why would you rebuild a heap? It's to get rid of forwarding pointers, which is the fragmentation that you could experience inside of a heap. All right, so next up, we've got clustered indexes. You don't need glasses unless you already have glasses like me. That tree is upside down, and it's for a reason. It's an upside down B tree. It's much like hierarchical chain of command, where we've got a root at the top, and then we've got our leaves down at the bottom. So you can only have one per table. A table is either a heap or a clustered index. There is no in between. It doesn't have to be unique. Keep in mind, many people think it has to be unique. That's a primary key constraint. The primary key constraint has to be unique. Clustered indexes do not have to be unique, but if you don't make them unique, it adds something to it called a unifier. We'll get to that a bit later. It's got a B-tree structure. 0 is the lowest level. 1 is the highest level. If you build your index so big that it has multiple pages, it'll have multiple level 2s. Those are your intermediate pages. But 1 will always be your root. 2 will be your intermediate levels if you need them. And then 0 is your leaf level where the physical data is actually stored for your clustered indexes on the pages. So some best practices for optimization. We want our clustered indexes to be narrow, static, unique, ever increasing. If you stick with that, you're good. I mean, so what's that? That's an integer value. That's a big integer value, depending on the number of rows you believe you will have. Remember, every database yearns to grow up and be a very large database. And so sometimes it's more important to use a big int key. I know we all go, oh, I'll never need that big int key. But if you ever have to reseed an integer table so you can now use big ints because you stopped at the 4.2 billion, whatever number it is, that is a painful process. So you're basically trading 4 bytes for 8 bytes. So if you have any inkling whatsoever that you can constantly add values to a table, and also keep in mind, you can start at negative 2 point something billion, 4 point something billion for big int. We used to use negative values way back in the day when we'd have like an East Coast system, a West Coast system, where you had to reconcile them during the day. One would be negative numbers, one would be positive numbers, and that's how you knew which was on which side of, you know, where. When we had to, when internet lines were, you know, not as good and disks were super expensive. And anyway, way back in the day when this was not white. So those are still the best case values. What's the worst thing you could have as a clustered index? A GUID. And look, sometimes that happens because you get stuck with a third-party COTS product, and if you could find the developer or the DBA who wrote that thing and get them alone in a room for a little while, you would show them a new world of pain. But you can't, and they're not going to change it, so you got a GUID for a key. So sometimes what you have to do with GUIDs is you have to look at the fill factor that you leave on your pages to be able to solve for the fragmentation that you have to have. So some of the issues are page splits that fragmentation can cause, updates that can cause fragmentation, and your remedies would be index maintenance, adjusting fill factor, modifying the key. Fill factor, real quick, is the amount of free space that you have, the amount of available space that you have on a page. So, sorry, I think I've got that backwards. If I set it to 80, that's the amount that's going to be used on a page, and I'll have 20% free space. I was working for the Obama administration. I'm the lead DBA, and I've got this system, and everybody who comes in for a White House tour has to get cleared by the Secret Service. They go in this system, and then it's at the front gate so people can come in. I have no idea if that's still the same system. I haven't been there in quite a number of years, but that's what we had. And that system was built by a third-party vendor that used GUIDs for clustered indexes. So I had to rebuild my indexes every day at noon in order for us to be able to use the system after the lunch break when people showed up for their tours. Otherwise, the latency was so bad it was unusable. The way that I got us through the day is I changed my fill factor to 20. So 80% of my space on my page was free during the day. So when new records came in, I had enough space that I was not fragmenting the table, but I had to rebuild it every single night. You are going to know your data better than me. And while I would love to tell you never use a GUID, there will be times you are stuck using a GUID. That's okay. And there are ways that we can mitigate and get around that. But just remember that best practice that I say, it's going to work for you some of the time, not going to work for you all the time, and that's okay too. So this is a B tree. If I said I've got a B tree of the alphabet and I want to write a query and I select star from alphabet where value equals H, I'm going to look at A and J, and I'm going to go H is greater than A, it's less than J, and I'm going to transverse over to this side where my intermediate page has A, C, F, and H. And then you can see I've got these leaf values. Well, I'm going to go H is greater than A, it's greater than C, it's greater than F, it's equivalent to H. I will transverse down the leaf level, and I've done 3 reads to be able to get my H value. And that's how our indexes work. We have these intermediate values, but the low value is always raised up because we use that as the qualifying condition to determine which path should we transverse to be able to get the data. But it's far greater than reading all of that data across the bottom. Wow, that didn't work for anything. So all the data across the bottom, pretend there's a circle there. All right. So non-clustered indexes. They have the same B tree structure. You can have 999 per table. This is not a goal. Not a goal. They can be placed on a heap or a clustered index. The size limitation of them are 1,700. As of 2016 and above, it was 900 bytes for 2014 and below. The B tree structure is the same upside down. Indexes have 0 as the leaf level. 1 and higher are non-leaf. 0 has our non-clustered index data. Pointers to the clustered index also has our include columns. If you ever hear the concept of a covering index, it's using include columns, so you don't have to do a lookup operation against the clustered index. Those are typical things that people typically look at. What is the expense of a lookup operation? So we could do a little bit of query tuning associated with it. The leaf level also contains either the row ID or the clustered index key. The clustered index key will point us to the leaf level so we can actually find it, plus a uniqueifier if required. If it's a non-unique clustered index, the row ID is a breakout that allows us to be able to find the page and the slot value that we're looking for on a heap. And so if we're looking at a query execution plan against a heap and we have a lookup value because we have a non-clustered index on it, we'll see a row lookup instead of a key lookup. So our best practices, we want columns and search terms, AKA where predicate values. We have foreign keys, intersection keys, and we might use the include columns for covering indexes. Now, one of the things that happens over time, and we'll get into this a bit in the demos, is that our knowledge base of our data warehouse atrophies. We create indexes, we put them in place for new functionality, we create more indexes, we put them in place for reporting. People leave and they find new jobs because they can get more pay, and then you leave that job because you can get more pay and somebody else inherits your job. And what do we have? Sometimes we have databases full of indexes and we're not actually sure how often they're being used and how well they're being used. And what we want to do is look at the expense of these physical structures and make sure that we're just maintaining the ones that we want to maintain. So this is going to be our first demo. This is an indexing internals demo. This is what I like to call a demo by PowerPoint, simply because I found if I do this in SFMS, when I flip around between the different query windows, it's a little bit harder to understand, but I can put the screens on here. The demos associated to this, I believe, if everything's not for download on the conference website yet, it will be. There's a demo folder. This is going to, everything demo by PowerPoint is going to cover the 0-1 demos on heaps and clustered indexes. Everything else I'll just execute on my machine. I'm going to use dbcc ind and dbcc page. These are old commands. We have DMVs that could theoretically replace them, but I don't get the exact same output I would like all of the time, so I'm going to use these commands because I'm old and I like them. dbcc ind is going to allow me to be able to transverse the index allocations. dbcc page is going to let me break out the pages to be able to look at the page data. You have to execute dbcc trace on 3604 in front of dbcc page, otherwise you won't get an output. It'll say, oh, you executed a command, see your administrator if you expected results. You can't use dbcc page and ind on Azure SQL Database or Azure SQL Managed Instance. You can on a VM just fine. The DMVs that have taken the place of these two items are what you would use to be able to look at this data on Managed Instance and Azure SQL Database. I did something very similar to this last year using Managed Instance, using those DMVs. So it's completely possible to do it, and you can find it on the SQL Bits YouTube site. All right, so the first thing I'm going to do is I'm going to create a database called demo indexes. I'm going to use demo indexes. And then what I'm going to do is I'm going to drop my table if it exists. I'm going to create my cluster table. This is starting out as a heap. I've got two columns, my ID, an identity value, but it's not a primary key, so there's no constraint on it. Oh no, sorry, there is primary key clustered on this. My bad, because I called it clustered table. Should have read that, because I call it heap when I use the heap one later. And then I've got one other column, my char, varchar 3500. I'm replicating A 3500 times, so it's using all the space. And I can fit two of these on a page. So a page has 8,060 bytes. And this is going to be 4 bytes for the my ID, 3,500, so we got 3,504. So we're going to be at 7,008 bytes. I can't get another record on any of these pages. I'm going to go ahead and I'm going to insert two values. We're going to do a dbcc ind on demo indexes and look at the clustered index table. And then the next thing I'm going to do is I'm going to do a dbcc ind before and after and do one more insert. And the reason I'm going to do that is if we've got two values, we're so small we don't actually need a root yet. And when we split it, we're going to have a root and we're going to have 2 pages. So this is what it looks like. And sorry, I know that's a little bit hard to read. I was trying to get the entire column in, but you can see page ID 465 up at the top. 465 is my page type 10. That's my IAM page. That's what a page type 10 means. And 472, that's my clustered index page, right? So you can see it's a 1 right there. And I don't need anything other than that. This is so small, if I made a root page, I'd have 2 pages in the table. Why do that when 1 page would satisfy it? I insert my rows, and now you can see I've got a page type 2, and I've got page type 1s. My page type 2 is going to be my non-leaf level. You can see on the index level right next to it, the 1s are at level 0. Those are my data pages, and the 1 is my root page. And so 272, 274, those are my root pages. 273, that's my, 272, 274, those are my leaf page. 273, that is my, my root page. So now I'm going to do a DBCC trace on 3604, DBCC page. I'm going to do a friendly output style 3 for that page, 473. That's our root page. And what I see is, there it is, referencing 272, 274. And you can see that first, my ID column is null. The next value is 3. This jives with what I said, right? I inserted my rows. I did 2 values. That'd be 1 and 2. Then I did another value. That split it. That's 3. So the low value on the page is 3 right there. Why is the other one null? It's null because that's a harken back to what I told you about the negative numbers. It is null because if I went in and inserted identity negative values into that index, I can do that. I could add those operations. And that would then need a low value for that page. But it's null until negative values are inserted that go to the other side of that page. So let's go ahead and insert 3 more rows. So what's that going to do, right? We've got 1, 2, 3 in there. So that should add value 4, 5, and 6. We should get another data page from that. And if I do a DBCC IND again, I can see I now have page 472, 474, 475. And again, there's my low value. We've got 6 total rows that have been installed. Low value of 3 is up. Low value of 5 is also up. So the next thing I want to make sure that you understand is when you rebuild a clustered index, you are reallocated all new pages, support pages and everything. This is a fully logged operation. If you've ever rebuilt a very large table and you've seen your index, your log file grow, or your log backup hasn't finished as you were doing a rebuild of an index, and then the backup for the log file is absolutely massive, well, that is the number of pages and rows commensurate with the size that you had on physical disk of that index. How big should your transaction log be? At least double the size of your largest clustered index. Otherwise, you'll fill it up while you're rebuilding it. Because as I rebuild, I've got to keep the space for my old index and my new index. So there are our numbers, right? The ones we've grown to know and love. 465, 72, 73, 74, 75. I do my rebuild, and now my IAM page is 466, and I have 480, 488, 489, and 520 as my new values. Those pages, while the data is there, are completely new and rebuilt. And so it's important to understand when we do that, everything is reallocated. I was working with a DBA recently, really, really great guy. We were doing a migration into Azure, and one of the things that he said was, well, I've got to drop the clustered indexes, and I've got to put the indexes back in place in order to rebuild them. And I was like, nope, we should just rebuild them online as an online operation, so that way we can get into the database faster. And he didn't realize this. And I went, no, let me show you this. And I showed him, yep, when we rebuild the index, this is, we're getting all new values. I think he was confusing a rebuild with a reorganize. And the reorganize, what do? We shift around the pages. If rebuilding an index is like moving from one home or apartment to another, then reorganizing is redoing all of your furniture, just putting it in a new pattern, changing everything. And that's what we're doing with a reorganization. We're not allocating new pages. We're trying to free up free space as we rebuild. All right, so next up, we're going to look at a heap. I've got create a heap table. I'm going to put 15,000 rows into this heap table. You can see I'm adding a value, but I don't have an identity. I'm actually inserting the identity value as we go through the loop. And then what I'm going to do is we're going to look at performance. I'm going to do a DBCC drop clean buffers. Don't do this in production. This is my demo environment. This will drop all the objects that you have in memory, execution plans, pages that you've read into memory off the physical disk. This is good to play around with. Even in dev, if it's a big environment, you got a lot of developers using it, maybe give people a heads up before you do this, right? But I'm doing this so that way you can see, I can measure the IOPS specifically. I'm using set statistics IO on. I'm saying select star from DBO heap where my ID equals 10. I only need to read one row. I'm including my actual execution plan. I'm getting my one row back. And this is a full table scan where you can see it's saying, hey, you're missing a non-clustered index. I'd like you to have a non-clustered index on this table because this would be much more efficient. And when I look at the IOPS on this, what I can see is that I have 7,504 logical reads, and I have 869 read-ahead reads. The read-ahead reads is the read-ahead read mechanism on SQL Server that optimizes reading those 8K pages off of a disk, and it reads them as 64K pages instead of an 8K page. So I wanted one row, I read the entire table. So this is every operation on a heap is a scan. So I'm going to set my IOPS off. I'm going to create a clustered index, do a DBCC drop clean buffer, set statistics IO back on. I'm going to do a select star heap. By the way, if you don't turn the statistics off, it just reports it on every operation. That's why you do that in the demo script. It's like accidentally rebuilding an index or doing something like that, but leaving your actual execution plan on. It runs longer because it's got to generate that, and then you go, oh, God, I should turn that off the next time I run it. So I'm then going to do the exact same operation, select star from DBO heap where my ID equals 10. I get the row back. It's a clustered index seek. And you can see I had 4 logical reads and 1 physical read. In Azure, one of the most important things you need to do is understand IOPS and the way that IOPS work on your Azure SQL database, your managed instance, on your VMs. It's almost like traveling back in time about 20 years. Because on-prem, what did we do? We bought tons of SSDs with ridiculously fast speed, and we networked directly to it. Well, I got news for you. That's not actually a disk in Azure. It's kind of like the Matrix, right? Oh, you think that's air you're breathing? No, that's code. There are JBODs and compute towers, and we provision those things there. And then there's networking components between all of them. There's no actual Azure SQL database sitting in there. It's all code sitting on top of Azure. Same with Azure SQL MI. Same with your VM. It's all just code. So what do we got to do? We got to optimize those IOPS. And it's really, really key to understand how this stuff works so we can make sure those IOPS are very optimized. Okay, so next thing we're going to do, DBCC IND looking at the heap. 1,000 rows, right? So there's a lot of pages in there. I don't expect you to look for all those. I'm going to look at this row specifically, 8,816, and I want to look at this a little bit closer. So I'm going to look at page, I'm going to do a DBCC page, look at this, and what I'm going to find is that here are my different heap informations, because I'm on my clustered index, right? Sorry, I keep saying heap because I didn't rename the table, my apologies. This is a clustered index, and you can see here's the my ID column, and that's the key column right there. That's what's sitting inside of that index page that we're looking at. And you can see here's the next page. Here's the individual pages we're looking at. Here's the row, 0, 1, 2, 3, 4, 5, 6. And then I can see based off the number, the size of the records, the low pointer also pointing up. So let's drop the index, drop the clustered index. We're going to create a non-clustered index. I do it on the 3,500 character column. And what do I get? I get an error because just like we said, this will be the error you get. You got to create it in under 17,000 bytes. So let's retry it on the other column that was smaller. That creates just fine. And now what I'm going to do is we've dropped the clustered index. We are a heap again. We've got a non-clustered index on there. And I'm going to do a search on that column I created. And I'm going to select value B101. I'm going to get that column. You can see this is a non-clustered index seek. And if I want to retrieve all the rows, you can see now I have that RID lookup that we kind of talked about, where I was like, this is a RID lookup. This is what's happening underneath the covers for a heap. So let's take a look at that a little bit closer. I'm going to look at the sysobjects and sysindexes DMVs to be able to find the index ID associated with this. I'm going to do a DBCC IND on table heap for index ID 3, which is my non-clustered index. And then what I'm going to do is I'm going to get that back. Now, I can see if I come across on value 800, it's an index level 1. So 0 is my data, 1 is an intermediate, 1 is my top root, and then 2 is an intermediate. So when I take a look at this page, I'm going to see, here are my child pages that I'm referencing, here are my key values that I'm referencing, and then there's that heap RID that we talked about. That value is in hex. It says, this is how you find me. This is the page, and this is the slot. The slot array starts at 0. Keep that in mind. So let's take that value, and let's actually break that out. I've got a script. This was written in a blog by a brilliant lady named Kaylin Delaney long ago. Kaylin is actually an absolutely wonderful MVP. If you've ever read any historical SQL books, at some point in time, you probably picked up one of Kaylin's books. I didn't write this, she did, and she's brilliant. That's all I wanted to say. So I'm going to take that value, and I'm going to put that into this, and I'm going to break it out, and I get page 13,563, slot 1. And so now I can do a DBCC page. For that, I'm going to get a lot of these values. Remember, I replicated a lot of white space. That's what 20 means in ASCII. It's white space. But you can see there's slot column 1, and I can see there's my ID, 904. And that's exactly what we were looking for, B904. Real quick, whenever I have a RID lookup, that's what I'm doing in SQL Server. I'm looking at the hex. I'm breaking out the hex. I'm going to the location where the data is. I'm reading the rest of the rows in that slot array with that. That's why this is an expensive operation. Now imagine if I have 2 forwarding pointers in place where I've got to hop twice to be able to get that data. That's also why and again, I don't want you to do lookup values on a heap, but if you do, this is why you're going to have to rebuild those heaps occasionally to make sure that you get rid of those forwarding pointers. So real quick, let's do a demo with a uniqueifier. So I'm going to set my statistics IO off. I'm going to create a new table called students. There's a lot of information I'm going to put in the students column. I'm going to try and make it really, really random, and I'm going to get students. So now I'm going to do a DBCC IND. We're going to look at students. Here's all my different values, and I'm going to create a clustered index. Sorry. I thought I had violently killed teams beforehand, but clearly I did not. So you can't kill teams nicely. You can't say, please don't pop up. You have to kill it violently. So I'm going to create my clustered index. I'm going to put it on first name, which is non-unique. And then I'm going to come in here, and I'm specifically going to get an index value of page 816. I'm going to do a DBCC page of that. And when I break this down, you can see here's all the first names, Chad, David, Jorge, Joss, and there's the uniqueifier value associated with it. Now, here's something to keep in mind for a non-unique clustered index. A uniqueifier is an int. You cannot make it start at a negative value of ordering, and if you run out of uniqueifiers, you can't add any more data to the clustered index. So, if you are ever in that situation and you need more than the 2.4 billion limitation in integer value, just keep that in mind, that you need to make sure that your non-unique clustered index only has that number of rows associated with it. That's typically why we say unique, narrow, static, ever increasing. Okay, so that was the demo on internals. Let's talk about how we measure performance and make good changes. So I've got a set statistics IO on. I've also got time. That measures CPU processing. Looking for seeks versus scan, which is filtering the number of rows, and making sure that we understand, am I using an index? Am I getting seeks with an index, or are we scanning the index every single time, which tells me it's good enough for us, the query optimizer, to be able to use it, but it's not unique enough for us to be able to do a seek operation on it. Index usage. We want to understand how often is the index used. Use the actual execution plan, use the query store, look for planned regressions. You can also use plan compare. There's also third-party tools out there, but I'll be honest, post-COVID, it's kind of hard to keep up with, what is still offered and what used to be offered. But there were some really good ones that were free for a while. All right, so let's look at the index column definition position. I'm going to create this demo composite index. I've got a lot of data I'm going to throw in here, a subset for myself, a lot more for some of my other friends. And then I'm going to define a non-clustered index. Now, sometimes people have told me I need to put the clustered index definition in the non-clustered index to get it to be used. That is completely incorrect. And I'm going to show you why. So this is my non-clustered index definition, but this is my key definition on my table. You can see this is the clustered index. I'm redefining it, and lower down, I'm using first name, last name as my search conditions for this non-clustered index. Let's go ahead and create it. My first query, I'm going to set all this on every single time, so I won't read it. DBCC drop clean buffers, statistics, time, and IO. I'm going to say select my ID first name from my table where my last name equals Ball, my first name equals Bradley, include the actual execution plan. And this is an index scan that comes back. When I look at this, I've got 4,752 logical reads and 47 read-ahead reads. Very inefficient for me to be using this index. Next one, select my first name from my table 1, where my ID is between 8001 and 8020. This is an index seek. Great. I've got 3 logical reads, and it didn't even register, even though I did a DBCC drop clean buffers. Sub-optimization, but it works for this query, right? Okay, now I've got select my first name, my last name, my date, my nickname from my table, where my first name equals Bradley, my last name equals Ball. This actually required a parallel plan. And when I look at this, I can see I had multiple tables because there's a work table needed for the parallel plan. And I've got 5,072 logical reads, 47 read-ahead reads, and my processing time is much higher. So clearly, this index is not working for these 3 queries the way I would like it to. So I'm going to come back here. I'm going to comment this out because I don't need this in my index. The clustered index is stored at the leaf level of the data, so if I'm trying to get my ID, my date, or my chart, it's going to get returned anyway because it's part of the clustered index, and it's at that leaf level at the non-clustered. So I'm just making a non-clustered index with first name, last name. I'm going to rerun this query. This is the old plan where we had 4,752 logical reads, 47 read-ahead, and now we had 4 logical reads. And we had, let's see, I don't think it registered. Next up, I've got my ID, my first name. Let's look at the execution plans. It was a scan, it's now a seek. And that's the kind of things that we're looking for to be able to measure, was this successful running this query? Next up, we're going to go to this one. Remember, it ran really well first time. We had 3 logical reads, and this time we have 3 logical reads. Okay, so there was no difference whatsoever. We didn't regress. But the big difference is last time I was using a non-clustered index seek. This time I'm using a clustered index seek, which makes sense. I already have the clustered index. It's going to satisfy this query. I should just use that. So next up, we had this one, this big monster right here. This was 5,072 logical reads with a work table, 47 read-ahead reads. Now we're at 64 logical reads. Didn't need a work table. As a matter of fact, when we look at the execution plans, we can see a much simplified, non-parallel plan to be able to look up this data. So what does this tell you? The data that we had before on that index, the scans would have way exceeded the seeks. And we should look at that and go, is this index operating the way that we want it to? Clearly the answer would be no, and we should rethink the way that we're utilizing it. Now, what do you have to do when you look at this? You got to look at the queries that are using an index. You do. Sometimes you can pull that from syscache plans. There's some different ways you can get that. You might be able to get that out of the query store as well. But you're going to have to do a little bit of working to go what queries are using which indexes. But if they are used often and in memory, they'll be there. All right, so indexes. Some issues that we have: duplicates, overlapping, missing or unused, and fragmentation. Our remedies are to be able to consolidate duplicate indexes, eliminate overlapping indexes where possible, evaluate missing indexes. Remember, 99% is not the high bar measure. I have seen query plans where we had as high as 14,000, 1,400, 1,500, 3,600, all represented at the values where an index could increase. So there's not a 1 to 100% on this. So don't think just because, oh, this is going to improve performance by 99%. that might not actually be the metric you're going to if you've got another index you could utilize that would increase performance by 1,000%. Fragmentation, index maintenance. With a bad index key, we already talked about this. Remember, maybe change the way you're using fill factor. You know your data best, or follow the best practices. Paul Randall will gladly tell you, if you ever see him at a conference, that he pulled them straight out of his pocket and took a swing. But they've been pretty good for 80% of the stuff that you've got, and they've stood the test of time. And so what are they? Well, you're going to reorganize. If there's less than 30% fragmentation, you're going to rebuild if there's greater than 30. But if you know your data and you need something different, that's your best practice. Document it and go for it. Document it so that way whoever inherits your job doesn't have to figure out why you made the decision. Rebuild recommendations. Recreate the index with the current properties, sort and temp DB options. Make sure you use online operations for clustered indexes. If you ever want to mess with somebody, do it in a dev environment, but disable a clustered index and have the new DBA try and select from the table. You can't do it. So when you rebuild the clustered index, what happens? It blocks everything because it's a fully logged transaction and you can't access the table. So if you need to access and you need to rebuild online. There's many scripts available, as the slide says. OLAs. Do not rebuild objects with less than 1,000 pages. Doesn't matter. You're not going to get a performance bump out of that. I was told that years ago by people on the SQL Server product group. I've not been told anything to the extent that that changes. So use that as a measure. Don't rebuild if it's less than 1,000 pages. Index metadata. Look at the index metadata. Look at seeks versus scans, reads versus writes. Do we need to maintain all of these indexes? Kimberly Tripp had a wonderful talk that she has done for years where she says indexes are like rain jackets. If it's raining outside, I'm going to put one on. If it's sunny, I don't need a rain jacket. Why would I maintain my end of quarter, my end of year processing job indexes all year long for the overhead and the IOPS and the updates on these tables when I could just drop them after they're done and then rebuild them in some maintenance window beforehand? Every single index is its own physical storage structure, takes up space on disk, and it affects your ACID properties, atomicity, consistency, isolation, durability. That consistency, data must be in a consistent state before any transaction can release the lock on that data. That means that all of my non-clustered indexes are on a table must be updated before I can release a lock. So what does that mean? If you have 999 indexes on a table, we got to do 999 indexes if that column is in every single one of those indexes. That's why you want to make sure you juxtapose what do you need versus what you want. So all this, I've got some more demos. I think we're very close on time. Those are going to be the remainders of the script. I've got 5 minutes, so I'll try and go into a couple of them real quick. We'll see if we can get this. But just to let you see what we've got. Sorry, these are for far away, not up close. You can see finding duplicate indexes, missing index stats, and then I've got some column store stuff in there as well, because even though I said we wouldn't get to it, if I have extra time, I like to try and get to it, because they are very important for performance. So let's see, set up for the duplicate indexes. Let me run that one real quick. And then what I'm going to do is I'm going to look at the duplicate indexes, because you have all probably seen and experienced fragmentation. This one would help if I was in the right database. There we go. All right, so what did I just do? Let's look at this script real quick. I've got the person.address table, and I just created a whole bunch of indexes, and you can see there's an original, there's a duplicate. If I look at this, right, very similar things. Reorderings of the address, line 1, overlapping, things of that nature, because what I'm trying to do, I don't know where my mouse went, so let's go right here. There we go. Okay. So I'm trying to create some of these indexes that we wouldn't want to maintain on a table. So what this script does is this loads some metadata into a temp table. It lists the different indexes. Now, I just started this up and I just ran this. I didn't have a workload running against this. In order to get some of this metadata, you need the items to actually be warm and to be in memory. But you can see right here, I've got a list of all my indexes. It did find redundant indexes. And what I'm looking for is how am I actually using these? Now, sometimes if you find a reverse index would be somebody made one with first name, last name, somebody made one with last name, first name. And what you need to do is check and see if there's code using both of them. And if there is, you probably change the stored procedure or you change the query if you can, and it's not a third-party COTS product, to be able to call things in the right order so you can always use the same index and you drop those reversed indexes. Duplicate indexes are, I've already got this index and this is going to satisfy one query and it's going to satisfy multiple queries. Let's drop this. I've been in places, and again, God bless developers, right? I need you to make apps to put data in my databases, so I have a job. I really appreciate you. But at the same time, sometimes you go to a shop where there's no DBA, and developers do things like use the index tuning advisor. I managed not to throw up when I said that, Eugene, if you make a note of that. That was really good. And then they'll apply the findings over and over again. Because what does it do? It looks at your missing indexes, your missing index stats, and every single time it says, take these missing indexes and make these missing indexes. And it doesn't bother to say, oh, you know what, we're good. Nope, if there's a missing index stat, and a missing index stat, just so you know, is I said, here's a where predicate value that we have on a table. I take that, I do that, I don't have an index for it. The query optimizer goes, hey, you could save X% if you put an index on this table based off the statistics that I currently have in front of me. And the index tuning advisor will go, oh yeah, missing index, I should absolutely make that. I had one customer that had about 350 indexes on a table, and they didn't understand why initially it made things get better, and then the performance just got worse no matter what they did. And 90% of those were duplicates. We actually took that table, which was about 250 gigs at that point in time. We got it down to 18 gigs just by dropping the number of indexes that we needed to drop for them. And their performance got a lot better. So before you go, there's no way anybody in my organization did it. Stop and say, have you built every database ever for your organization? And if you have, good on you. You've been there a long time. I hope they're treating you right. If you haven't, there's chances you've got a database somewhere that has some issues with some indexes that could be sorted. All right. But all those scripts are there for you guys to be able to take advantage of. So I'm just going to hop back in here. This is everything we covered. I've got some videos up on the Tales from the Field site. I've got one where I cover just all the concepts of internals. I've got another one where I cover a whole bunch of demos. So please feel free to go and watch those. Again, I've got stickers up here. This is the feedback link. This is always helpful. If this was good, let me know. If there's something you'd like to see in the future, I'm also completely open to that. This helps evaluate whether I come back or not. So be kind, please. And then that's Tom Hanks. So thanks. Appreciate you.